One has to do with a homework problem that I was helping a student with, and I noticed a discrepancy with mastering, so I just wanted you to be aware of it. Your numbers might be different. The reaction's the same, but your numbers might be different. It's asking, it doesn't matter what LP is. I don't even know what they mean by LP. It doesn't matter. But this thing, C3H8, it wants to know the amount of heat for 1.8 liters of water to increase the temperature from 25 degrees to 100 degrees. So it wants to know how much heat from this reaction, or how much of this you need to generate enough heat here to make water boil. That's all it's asking. The discrepancy comes from when I worked it. It's telling me I have 1.8 liters of water at room temperature, which means it's a liquid, right? So its density is 1 grams per milliliter. So that means that you really have 1,800 grams of water. But when I calculate it, it wants me to calculate it like I had 1.8 grams of water. So I don't know if they meant to put milliliters, or if they're wanting me to use the density of water as a gas, which doesn't make sense because at room temperature it's a liquid. So just when you're going to work this one, just change liters to grams. And I don't know why that's the case. And you should be able to do this problem because you can calculate the amount of heat needed, and then you know the amount of heat the reaction gives off. So you could figure out your mass of C3H8. The only trick is only 14% of that energy is going to water. But for some reason, I don't know, but it wants you to use 1.8 grams or whatever. You might be given 1.9 or 1.7, I don't know. But it wants you to use that as grams. And it's not, because the density of water is 1 grams per milliliter, not grams per liter. So I don't know where they're wrong there, but when you're working that one, just keep that in mind. But you should be able to work that one. The second thing I wanted to talk about was this. This was an example from the quiz. I wanted to know the delta E of a specific system per mole of aniline. And the question might come up, when do I use the mass term in Q? Well, if we're using specific heat, it is related to mass. So typically our specific heat will be given to us with the units, joules or kilojoules, depending. Actually, that's what I did wrong. Never mind, ignore that problem. That 4.18 is joules per grams degrees C. So this is kilojoules. That's where I went wrong. So this is 1/8,000 grams. Make sure when you're writing your units, you're using the right ones. So ignore everything I just said about this. This is right, but this is joules. So once you get this in joules of energy, you're going to have to convert it to kilojoules. That's why I was off by 1,000. Anyway, always follow your units. It'll help you from making a mistake. This is joules per grams degrees Celsius. So when we use a specific heat from this table, we have to multiply it by our mass to get rid of that grams term. But with our C-cal, typically our calorimeter constant is determined minus or normalized for the mass. Because a lot of people try to take the mass of aniline and multiply it by the C-cal by the change in temperature. First off, this is wrong. That mass is not your mass of your calorimeter, it's your mass of one of your reactants. Your calorimeter mass is a lot higher because your calorimeter has more than just one reactant in it. So first off, that's incorrect. You couldn't use that mass term anyway. But second, the C-cal doesn't have mass. So if you're following your units, you don't need to multiply it by a mass term to get your kilojoules because there is no mass term in that unit of that specific heat of the calorimeter. So you have to pay attention to your units. You don't really need to memorize when to use this versus when to use this. Just look at your constant. If your constant has a gram in it, you have to multiply the mass. If your constant doesn't, you don't have to multiply by the mass. Also remember your delta E of your calorimeter. Delta E is heat plus work, but work is 0 because your calorimeter is kept at constant value. So a lot of you tried to find work. Work is 0. You don't have to find work because your change in volume is 0. So work is equal to P times delta V. Delta V is 0, so P is 0. Work is 0. But following your units will help you from making a mistake. And it's just really how we find CCAL. We basically don't normalize it to grams. So you have to watch whatever specific heat you're given, see what units it's in. If grams is part of that term, you're going to have to multiply by a certain mass, whatever you're given. If you don't have grams, then you don't need the mass to calculate your Q. So look at your units. You can always follow your units in this class and figure out what you need to. And figure out if you're doing something wrong or not. Like I just did here. So now going from that, let's go back to what we were talking about for our standard enthalpy. Now before I go on, I just want to point out we're able to use Hess's law with our heats of formation to figure out our delta H reaction. But this only works if we're using delta H formations. So a couple of the examples I showed with Hess's law before that didn't have to do with heats of formation, we can't use this. This only works if we're using heats of formation, this particular equation. So some of the examples, if you're not using a heats of formation one, you then have to use Hess's law. But Hess's law works both for both of these, and we went through examples of those. But we can also apply that to our reactions. So again, the reason why we might do this with these standard state, why we might use Hess's law is it might be really hard for us to calculate our delta H of our reaction, but delta H's of our formation reactions are often readily available. So if we know those, then we can figure out our delta H of our reaction without actually measuring our reaction. So that's its usefulness. So that's how we can use that. And again, that equation's only for heats of formation. If it's not a delta H of formation, you can't use it. Now we can actually apply this to chemical reactions. So we're going to look at some examples of when using this delta H reaction is going to be applicable in the lab. And we're going to do that by looking at a couple of examples. So let's say we want to know how many kilograms of octane must undergo combustion to supply 1.0 times 10 to 11 kilojoules of energy. So that's our surroundings, of course. Our surroundings, the energy is increasing. So if we know our delta H of a reaction, then we can figure this out. So we're given that we want to know how much octane to form 1 times 10 to 11 kilojoules. So our conceptual plan, we know our millimoles of octane. And we can write our balance equation. Oh, I know why that's not supposed to be there. We're not given this yet. I thought I deleted that. Okay. So we're given this. We're given our mass of octane. But we don't know our delta H of octane to calculate. But we can figure it out. So we know our molar mass of octane. We want to write our balanced equation. Now first off, if I gave you octane, I have to give you the chemical formula. Because you're not in organic chemistry, so you probably don't know it. I know it because I'm an organic chemist. So if I ever give you an organic name and I don't give you the chemical formula, feel free to ask me for it. I'm not expecting you to memorize it. Sometimes it's an oversight for me because I know what octane is. But you aren't necessarily to know what octane is. You haven't learned how to name that. I would have to give you the chemical formula. So just keep that in mind. It's CA H 18. 16, 17, 18. C8H18. It's CnH2n plus 2. Again, organic chemistry, you don't need to know that right now. I would give you the chemical equation. But we do have to write the formula. So first off, you know it's combustion. You would need to know what octane looks like, and you can figure out your combustion reaction. If we know our combustion reaction, we can then use our delta H of formation to figure out our delta H of our reaction without actually doing a chemical reaction to figure it out. When we have our delta H of our reaction for 1 mole of octane, we can then figure out how much octane we need to supply that much in the lab. So here we're applying what we learned. So our first step is going to be write our combustion reaction because we need to know our coefficients. so we can figure out our delta H of our reaction. So that's going to be our first step. If we can't write our reaction, then we're going to have an issue. Once we have that, we can figure out our moles of octane. So first we got to write our chemical reaction. Now, I want to know my heats of formation for 1 mole of octane to make it simple. So when I balanced it, it would be 2 moles C8H18, 25 O2 gives us 16 CO2 and 18 H2O. I just divided everything by 2 to make my mole octane 1. That's just to be really clear that I'm looking at my heat of formation of octane for 1 mole. Because remember, that has to be in 1 mole. So that's the only reason why I did that. So I just balanced it by normal, and then I just divided everything to make my mole of octane 1. And again, I would give you C8H18. You don't have to memorize that. So we know combustion is our carbon-containing compound plus O2 to form CO2 and H2O. You should be able to write that reaction if you know octane is C8H18. That's something you should be able to do. So now we can figure out, by looking up our heats of formation, our delta H. Now again, you could use Hess's law, but we're just going to, from now on, use the equation. So I can look this up. And this is just looked up, so I put them nice here. If I gave this to you in a test, I'd give you this. I'd give you the chart to look them up. One note, though, H2O gas and H2O liquid are different delta H formations, so you need to make sure you're using the correct state for that. Because otherwise the number is going to be different and your answer is not going to be right.
Is that going to be dangerous on the test?
Yeah, you won't have to memorize this. Well, you should know that if it's an elemental form, it's 0. You should know that. So I don't really need to give you O2 gas. That's elemental form, so we know that's 0. But anything not in elemental form, yeah, you don't have to memorize it. But I might give you H2O liquid and H2O gas, and you have to decide which one. So remember, combustion always forms H2O as a gas. It's really hot. Giving off a lot of heat, so H2O is in the gas form. So that is a different number. That's the only trick. So now we can figure out our delta H reaction. It's just our sum of our delta H formations of our products minus our sum of our delta H formation of our reactants. And that's just because when we look at our products, we have to switch them. So that switches the sign. So that's why it's that way. You have to make sure it's products minus reactants. It's very important. And we're just going to put our coefficients in the front. So, where's it keep on going back? I thought it was just me, but one of my students gave a presentation in here yesterday, and he was having issues with the PowerPoint slides too. So apparently it's not just me. I don't know what's going on with them. So our delta H of our formation. There we go. I lost my numbers. Is going to be 8 times our delta H formation of CO2, which is negative 393.5. The 8 is just that coefficient. Plus 9 times our delta H of formation of H2O gas, which is very important. Minus, and I'm going to put this all in parentheses and take my minus later because it's really easy to make a mistake with the sign here.
I have a question.
Yep.
Where did that 285?
Oh, I was looking at the wrong one, sorry. 241. 285 would be it in the liquid form. So minus my 241, again, you want to double check that. And then I'm just going to keep my minus here so I'm not making a mistake with my signs later. So my 1 mole, I'm going to put the 1 so when you're looking back you see it, but of course it's not necessary. Plus, of course, 25 over 2 times 0. which is our delta H formation of our O2. And again, I know that's going to be a term of 0, but to be clear when you're looking back at this. So you might want to practice putting these in your calculator correctly, because this is going to be negative, but we're multiplying it by the fact that this is a minus. So you want to make sure, you might want to practice that you're putting this in correctly. You're not making a mistake with the negative signs and the plus signs and the minus signs. So you definitely want to practice these and double check your work when you're putting it in your calculator. But that'll come out to negative 5,074.1 kilojoules. And the negative is really important, but this is combustion, so you know it should be negative. If you don't get negative for a combustion reaction, you have a problem, because you know combustion is giving off heat. So you know that should be a negative number. And if you don't remember that combustion is giving off heat, just think about the fact that we use combustion to heat the room by burning different fuels. So you should always recognize, just using your everyday knowledge, that this should be a negative number. If it doesn't come out negative, you did something wrong. So use a little bit of your knowledge about what's going on around you. So what this tells me is, for every 1 mole of C8H18 burned, we form 5,074.1 kilojoules of heat. And we want to know how much kilograms of octane must be burned to form 1.0 times 10 to the 11 kilojoules of heat, which is much more heat. Now don't get confused, because this is a negative number and this is a positive, because what we're describing here is the surroundings. So that means that the system is losing negative 1.0 times 10 to the 11 kilojoules of energy. And this is just tying it into what we did before. We have that relationship, so we want to know 1.0 times 10 to the 11 kilojoules. We know that for every 1 mole, we form 5,074.1 kilojoules of heat out to the environment. So my kilojoules can cancel out. That tells me how many moles of C8H18 I need to form that much heat. You're forming a lot of heat, so you need a lot of moles. It's a big number. 1.0 times 10 to the 11. That's a lot of kilojoules. So now to figure out how many grams, I know my molar mass is 114.2 grams per 1 mole of octane. This is what we've been doing since the beginning of class. There's no difference here. And of course that's going to be a really big number, which is why it's asking for it in kilograms. So 1,000 grams is equal to 1 kilogram. And that's still a really big number, actually. Should be 2.3, but sometimes it's just about your calculator. So that's 5074.1. I know sometimes when I write on here, it doesn't come out clear. So that's how much kilograms of octane I need to make that much heat energy. So all you really need is to find your delta H, and you can use your delta H formation reactions. Let's look at one more example. I'm sorry. Calculate our delta H for decomposition of 10 grams of limestone. And again, here's limestone, and in this case I'm giving you the decomposition reaction. So CaCO3 solid forms CaCO solid plus O2 gas. So I want to know how much delta H, what the delta H is. I don't really know decomposition-wise whether this is going to be positive or negative, but how much delta H, what's my difference in energy when I decompose limestone? So I don't need that till the end again. My first step is to figure out, for 1 mole of limestone, what's my delta H? And I can do that again using my heats of formation. So the same thing, we're going to do my delta H of my products sum minus my delta H of my reaction sum. And I always want to make sure my reaction is balanced, and it is in this case, but I just want to make sure it is. So now I can figure this out. So now I can put this in.
Where's it?
I'm looking at that, and I think it's supposed to be C2 in the final form. No, carbon. Yeah, this is missing a term. And it should be carbon, and carbon in its form is the solid room brick. Which, of course, is going to be 0. That's not going to affect the work. But it's balanced now. But it forms carbon in the elemental form. Solid and then the room brick. Again, I would give you this equation. I didn't realize I lost a term there. It's not going to affect the overall work, though. And, of course, this is 0. So, again, we're doing the same thing. Find my delta H. If it's not given to me, I can find it. A formation is going to be my, and all of this is 1 mole, so that makes it really nice for the calculation. But my products minus my reactants. So in this case, it's going to be CaO. And these are all in kilojoules per mole. Plus O2, which is 0. Plus that carbon term, which is also 0. Minus, and I like to put this in my brackets when I have multiple terms in my reactant. So again, I keep that negative term throughout. I'm not just multiplying it by the first term, I'm multiplying it by everything in my reactants. I only have CaCO3, so it's not as necessary here, but it's really easy to make a mistake. This is really simple addition and subtraction. It's easy to make a mistake with the sign. So we want to watch out for that. So negative 1207.6. And we don't have any other term, so we don't have to worry about that. So of course that makes that term positive. So my delta H in this case is actually going to be positive. A formation for CaCO3 is going to be 572.7 kilojoules per mole of CaCO3. So that tells me for every 1 mole of CaCO3 that decomposes, we're going to need, because this is positive, to take in 572.7 kilojoules of heat, because it's positive. So the question is, how much delta H do we need for 10 grams? Well, how much moles are in 10 grams? We can calculate that because we've been doing that since the beginning of class. So 10.0 grams of CaCO3. We could calculate our molar mass. It is 100.09 grams of CaCO3 for 1 mole. Use your periodic table to calculate that. And now that I know how many moles I have, I can use my relationship of my formation for 1 mole of calcium CO3. I need 572.7 kilojoules. Of energy, which is most likely heat. There is a little bit more to that, but you'll get into that later on in 106. So fairly straightforward, and that's where those heats of formation can be applied. Instead of having to actually measure my delta H of that reaction, I can look it up by using my heats of formation. Oh, it might be 57.2. I have 57.3 written down, but I could double check it later.
Yeah.
Yeah, I rounded it to 3 significant figures. Okay. I don't want that here. So that is that chapter. And I do not know why that slide came up. So that's that chapter. And now let's go on to chapter 7. And we're finally getting a little bit away from math. There's not a lot of math in this chapter. Yay! Finally, I really rather teach this class once we get to this chapter because this chapter starts explaining everything that we've learned. And I really don't like the way this book is set up, but all the instructors kind of agree on one book. I can't just choose a specific book. But I really don't like the whole, hey, memorize oxidation states, if I could explain it to you. Memorize what ratio your calcium and your hydroxide are going to interact. I'm now going to explain where all of that comes from. And we're going to mostly explain this in chapters 7, 8, and 9. So chapter 7 isn't going to be really long, and I'm not even covering necessarily everything in chapter 7, just what I feel is the most important to get to chapter 8 and 9. So quantum mechanical model of the atom is really coming from PChem, and if you're a chemistry major, that is going to be a class you are going to take, and it's going to be interesting. If you're not a chemistry major, you're never going to take it, so we're going to condense a whole semester class into like 70 slides, because I'm not going to go into everything. I'm going to represent some things to you, and we're going to go into the background of the math, but we're not going to use the big calculus equation and actually do the calculations, because honestly, I can't do that. PChem is not my specialty, and I wouldn't even pretend to try to explain that to you. But I can explain the background of it and how we apply it to general chemistry. So when we talk about the quantum mechanical model, we're talking about quantum chemistry. We're representing the electron, something really, really small. And we're trying to represent it to explain what we can't see. And what we're going to mostly be doing when we're talking about this is discussing a big mathematical equation that we use to model how the electron moves and how it reacts. And what you have to understand is anything other than hydrogen that has more than one electron and 0 protons, one electron, 1 proton, and 0 neutrons, it gets really complicated, and it takes a computer a really long time to do. But we can still use these models, and we have, and it explains really well what we see in nature. So the other thing I want you to understand when we're using modeling is we're using what we see in nature, what we can visualize, and then applying a math problem to what we can't visualize, and then seeing if that agrees with experimental results in nature. So it's going to be a little bit abstract at times, but I'm going to try to explain it in a way that makes sense and for us to actually be able to apply it. But we're not going to do the big calculus equation, I promise. So first we got to talk about how matter behaves. So our first step in modeling how an electron is going to behave, how an atom is going to behave as a whole, is we have to understand how matter behaves. So we're first going to look at electromagnetic radiation, light and matter. Now the dual nature is that matter can behave as both a particle, it has particle behaviors, and we'll talk about what those are, and it can behave as light. So we're going to look at that. So light and matter are both single entities, and they have a duality that gives us limitation in how we can understand it, and that's by Heisenberg, which of course is the same scientist that came up with the nuclear law. Heisenberg did a lot of work with light and matter. He specifically was at nuclear chemistry, which is what's going on with the nucleus, but he also did a lot of this. So matter has both particles, meaning it has mass and it occupies space, but it also behaves as energy. So it has like behavior characteristics. So we're going to talk about matter in this dual nature, that it can behave as a particle or it can behave similar to light, and what we'll really say is it can behave as a wave. So we're going to have to look at particle as a wave and particle as its behavior as a particle. All matter possesses this dual personality, and we have to understand how these things interact. We have to understand this. So most subatomic particles are real small particles. Our electrons, our protons, behave as particles, and they obey the physics of light waves. The behavior is more prevalent because of the size of the particle. So the concept that describes this dual nature, we call it wave duality, meaning it can behave as a particle or a wave. And it is the theory that explains quantum mechanics. And quantum just means we're trying to look at something that's really small that we can't necessarily see, but we can still measure the effects of it. Just because we can't see it doesn't mean we can't measure the effects of what happens. So that's really what physical chemistry is studying the effect of. And we'll look at some ways of how it behaves as a particle and how it behaves as a wave and what that means. So just to remind you, if you don't remember from physical chemistry from high school, here's a wave. Our wavelength, lambda, which is represented by the lambda sign, is our distance from peak to peak. And our amplitude is our height of the wave. And then our node is the point where we reach that line. So when we're going to be discussing an electron, the point where the electron reaches that line, we're going to call that our point 0. And the answer to our equation is going to be 0. And then the answer of our equation, our big math equation, could either be positive above the line of 0 or negative below the line of 0. And we're going to call when it points to this line a node. That's where when it crosses 0. When we're describing the electron, that's going to be described as a 0 probability that the electron is there. So what we're going to be doing is trying to understand where the electron likely is in our atom and in matter. And when we talk about a node, there's a 0% probability that our electron is there. So this is all based on a mathematical equation. So our frequency is the amount of times that our wave passes through our node at a given amount of time. As our frequency increases, our wavelength has to decrease because then it has to go through more times. So that means that the distance between the peaks is going to be shorter. So frequency and wavelength are inverse proportional to each other. Now light, which is what electromagnetic radiation is a type of energy, and it embodies an oscillating electric and magnetic field. So our wave is on two different field planes. We have both a magnetic field, which is typically drawn on the x-axis, and the magnetic field, which is drawn up and down. So you can think about the electric field and the magnetic field just being parallel to each other, like this. But we have both wave functions there, and then that 0 point node is always the same. So our frequency, like I was saying, which is usually shown by the Greek letter nu, which looks like a V, but it's italicized, and it's usually in lowercase. And our frequency is the amount of times that our wave will pass through our node at a given distance. So higher frequencies, notice our wavelength has to get smaller, and larger frequencies, our wavelength has to get bigger. So the distance between light waves is referred to as our wavelength, our lambda. So they're related, but they're inversely related. And they are related based on the speed of light, because we are representing light here. So our units for lambda, for frequency, is either 1/seconds Our seconds -1 is our SI unit. You might see minutes, but when we're talking about wavelength, we're talking about fast. So we're usually looking at seconds. So if you see second -1, that means 1 over seconds because of the fact that it is inversely proportional to our wavelength. So some formulas, a little bit of math, not a lot. Our wavelength times our frequency is going to give us the speed of light. So we can relate wavelength and frequency. Notice our wavelength and our frequency are inversely proportional because, of course, as we increase frequency, wavelength has to get smaller. As we decrease frequency, wavelength has to get bigger. But it is related to the speed of light. That is a constant 3.00 times 10 to the 8 meters per second. So that's a constant. That's not going to change. That's just the speed of light. You don't necessarily have to memorize it. I'll give it to you. But again, it's kind of one of those that everyone kind of knows the speed of light. That does math because we use it so often. But I'll give it to you. So you do need to know this equation and how they're related. So which of the following best defines electromagnetic radiation or light? It's energy oscillating in electric and magnetic fields. That's what our light is. So again, our relationship, a long wavelength means we have a smaller frequency, and a short wavelength means we have a higher frequency, so they are inversely proportional. So we can say our relationship of wavelength and frequency is just the inverse of each other. So for example, red light has a wavelength of 700 nanometers. What would be the frequency? So first off, our speed of light is 3 times 10 to the 8 meters per second, but meters is pretty big. So we'll usually have to convert it to nanometers, so we can use that. So that's going to be our first step. This is given to us in meters. So our first step is, in nanometers, our first step is to convert it to meters. So in 1 meter, we have 1 times 10 to the 9 nanometers. So we use that conversion so we can convert it to meters. Then we can use our relationship using the speed of light to figure out our frequency. So 3 times 10 to the 8 meters per second divided by 7 times 10 to the 7 meters. Our meters cancel out and we are left with seconds -1. Bless you. So you can either write that as 4.29 times 10 to the 14th per second or 4.29 times 10 to the 14th seconds -1. Both are acceptable. If you're doing these in mastering, make sure that you pay attention to what it wants it in. It probably wants your units like this, but just double check because mastering is real strict about how you put things in. So make sure that it usually tells you somewhere how you should be putting things in. Make sure you put it in correctly. That's about most of our math that we're going to talk about in this chapter as far as applying it. So if you know your nanometers of wavelength, you can figure out your frequency. So that's pretty straightforward. And then that brings us to our light spectrum. So electromagnetic spectrum just illustrates the range of electromagnetic radiation. The classifications of different type of light are based on the wavelength. Short wavelength, meaning high frequency, has high energy. The more times you're passing through a point, the more energy is going to be released. So that means that we have a short wavelength, a short distance between our peaks. So what we're typically looking at that high energy range are radio waves and gamma rays. Radio waves have the lowest light and gamma have the highest. So we have a range there. Now the only part we see, what we call visible light, is a very small part of light. It's just this little bit. But we actually use a lot of these other types of electromagnetic radiation every day. For example, radio waves. Here's TV, FM, your cell phone is all in this part. AM is way down here. So that's your radio wave. Now those aren't dangerous to us. We have microwave, so when you're using your microwave, that's the energy of light you're using. And what we're looking at here is wavelength is smaller here, so this is our low energy, and then as we get here, our high energy, our high frequency. So, what we're representing the wavelength is 10 to the fifth, 10 to the third. Notice it's going down, but when we see frequency, it's going up. So that makes sense. That's just showing the inverse relationship. We're typically describing light by wavelength, but we can always relate that to frequency because we know it's an inverse relationship. Your ultraviolet light, UV light, is a bit above higher energy than our normal visible light. X-ray and gamma rays are high energy. You have to be careful with them. Of course, you know that if you've ever done an X-ray. And they cover you, so only the part of your body that they're X-raying is actually being looked at, because you don't want to be exposed to too much high energy of the light. And gamma rays are really high energy. So that's what we're looking at when we're looking at light. And what we see, our visible light, is only a small fraction, but we use a lot of this light. UV light is also something that we come across all the time because the light gives off UV radiation. So we do get UV radiation often. So that's also something that we have to contend with. So what's color? All electromagnetic radiation has color. However, not all electromagnetic radiation is visible to our human eyes. So color of light can be determined by wavelength or frequency, as long as we know the visible spectrum. White light is a mixture of all colors of light that's visible. So 700 to 400 nanometers is what we're looking at. And here's from, your physical science class: red, orange, yellow, green, blue, and violet. Color happens, not purple, but we call it purple typically, but it's violet. Color happens when an object absorbs some of the wavelengths of white light while reflecting others, and that appears as color. So, of course, that's where we use that color wheel to determine if it is absorbing in this wavelength, what are we seeing, that sort of thing. The observed color is predominantly our colors reflected. And I'm not going to get too much into color. I just wanted to get some of those. So the color and intensity actually are both a result of electromagnetic wave properties. So color electromagnetic radiation is determined by our wave distance. Intensity is determined by our wave amplitude. So how intense that color is. So it makes sense that what we're talking about is our wavelength or frequency to determine our different colors. But how brightness that color is actually dependent on the amplitudes of the wavelength. So, of course, as energy increases, wavelength decreases, so frequency increases. Remember, the more times you're going through a point, the higher the frequency, so the higher the energy. And then wavelength is opposite from that. Why am I telling you about this light? And because we want to relate it to wave behavior. And this is all going to relate into experimentation that was done to understand how the subatomic particles exist. So first we have to talk about two different types of interference. We have constructive interference and destructive interference. And you can kind of get a good idea of what those are just based on the names. So if your wavelengths align, or they're what we call in phase, then that's going to reinforce the amplitude. And that's what we call constructive interference. However, if our two waves are out of phase, then they cancel each other out somewhat, and that's going to be a destructive interference. And we can relate this to color and brightness, or we can relate this to how we understand our subatomic particles. So the next thing to understand some of the reactions that we're going to talk about, really look into how particles move. Now that we look at constructive and destructive interference, which is all going to be important when we're mapping out bonding, especially in organic chemistry, we talk about it a lot. We also have to understand a little bit about the behavior of diffraction. So diffraction is the ending of a light wave. It occurs when a light wave encounters an obstacle or travels through a slit similar in size to its wavelength. So what we see here, we have our wave, we have a barrier, and then we have the diffractive wave that comes through. Now, how does that differ from particle behavior? Particles don't diffract. If we take a particle and we pass it through a slit, either they're going to be stopped or they're going to go through the slit depending on the size, but it doesn't change the weight. So, again, the fact that our matter behaves as both a particle and a wave is going to be important to this concept, to looking at how it behaves and to understanding our experimentation. And it is, of course, dependent on wavelength size when we're talking about a wavelength.
So how do you distinguish the difference between whether it's a particle or a wave?
Again, all matter has both of those nature, so we're going to get a little bit more into that and looking at some of the experimentation that was done to understand our subatomic particles and how it's behaving. But when we're talking about the macro scale, what we see every day, if you're looking at a small door, I can't fit through it, but I can fit through that door. But if I try to run through a small door, I'm just going to bounce on it. When we're talking about the small scale, it's going to behave differently. So what we see in the large macro scale is different from what we're seeing in the small scale. So that's kind of where I'm trying to get you to. So I'm kind of telling a story with these slides, and I don't want to get ahead, because if I get ahead, it's just going to be confusing. So I'm trying to build up to the experimentation we did to actually define what's happening. And what you have to realize is when we're talking at the really, really small scale, that's what we're looking at. So light diffracts through two slits separated by a distance. If we're looking at a two-slit interference, let's say we set up a reaction, we have slits, and they have the two slits here. And then we have a second film here. But we have two slits, but we have a light that is able to span both. What's going to happen? So if it's a distance comparable to the wavelength, of course, if our wavelength isn't big enough to reach these two slits, this isn't going to be something we can talk about. But if our wavelength is big enough to reach the two slits, we actually get an interference pattern of the diffractive waves. So some of the waves go through this slit, some go through this slit, and how they go through and whether we're getting constructive and destructive interference is going to depend on what the wave looked like before and what, if we're talking about particles, or what our matter is made up of. So we can actually take a picture of a diffraction pattern, which represents waves and are made out of the dark spots, and those are waves out of phase that are having destructive interference, and waves that are having constructive interference gives us the light brighter spots because that's bigger, so it's brighter. So we're getting the bigger wave, the bigger amplitude. Why am I showing you this? The reason why I'm showing you this is it has been found that different atoms have different diffraction patterns. So that suggests that our atoms can behave like a wave. So that's where we're going to be getting to looking at our wave behavior. I'm going to let it go here because I don't want to give you too much information all at once. And we're going to finish this chapter probably on Friday.
So I have a question.
Yep.
So with the two-split interference, is that similar to what we see in X-rays?
So, hold on, let me.